Hello and welcome to the 8th episode of the RockyTerrain Podcast. Today is February the 18th, 2021, and we're recording at 19 p.m., so a bit earlier than the last times. My name is Thomas, and with me is always my good friend Dennis.
Hello there.
So, today is again kind of a special episode. I have the feeling that we say that every time. We're trying something new out for today, but we will talk about that later. So if you're interested into the question why it rains diamonds on Neptune or Uranus, then you're welcome to stay.
Yeah, it's, I guess, a pretty random topic, but we're gonna go into why this is relevant for geoscientists later on.
Yeah, we're going into that. Otherwise, today is a very special day. But I think I'm gonna talk about it once I'm into my introduction part. But before, Dennis, do you want anything? Is there anything you want to talk about in the podcast?
At the moment, everything is pretty boring in my life, I guess, because once again, nothing really ground shaking or anything. Today is the first time we're recording, or I'm recording with my PC. So we have effectively finally eliminated the lag and the delay. Because Thomas used to hear me about 1 second later than when I actually started talking, and this is why we kept bumping into one another. And yeah, this is gone right now, at long last.
Beautiful.
Yeah, before we started recording, he was like, something's different today, but he couldn't really grasp what it was. And yeah, it was that there was no annoying delay and that there actually were no lags anymore.
Yeah.
Yeah. So, yeah, that is new. We've said that on the last podcast. I edited the last episode. I hope I've done well. I don't know whether I've done well. I think it turned out pretty good. Yeah, but this is going to be the case more frequently because right now I have the capacity to do so, and yeah, otherwise, work in the collection continues, as I think I say every single time when I'm on here. But actually, what is kind of interesting is that right now, slowly planning for field trips is starting again, or maybe not even field trips, but planning for what we're going to do at our dig site in Balve.
With the museum.
Exactly. Of course, it's still a challenging situation. We're still not through all of this. And yeah, I mean, currently the feeling is that we are going to have restrictions similar to the ones from last year. We're still hoping that maybe we can participate in fieldwork, but it's basically, at the moment, it's a question of how many cars will we get, because the museum has a couple of cars ready. Two of them, one is a pickup and one, how do you say, in Germany, Mercedes Sprinter. Is it a van?
Van.
Yeah, a van type of vehicle. We have two of these cars for going to the dig site for, more off-road purposes. But currently, I think the discussion is whether we can use both simultaneously. When can we do so? So a lot of planning involved right now. Everything is, as I've said, we're still having the feeling that this year is going to be mostly like last year, where only 1 or 2 people can be at the dig site at a time, and the majority of the work will be done at the museum itself. But yeah, we don't know yet. Still, it's pretty exciting because, yeah, right now you have the feeling that everything is slowly reawakening in terms of field work. And yeah, who doesn't love field work, right? Because
one of the reasons why we go to geology.
Yeah, and I'm also planning to potentially go to the Nguyen Mountains in March, because it's been pretty cold over the past 1.5 weeks in Germany. We've had up to minus, I think, 12 degrees Celsius.
I think even lower. I thought it was minus 18 even.
Yeah, so it was pretty cold. And you know what extreme cold does is things freeze up and water in cracks in the rocks tends to break them apart. Because as soon as the water freezes, it extends. Yeah, and what it does is it pushes the rock apart, loosening blocks and potentially creating new blocks with tracks on them. So, yeah, the hope is that the winter might have revealed something new. We'll see then. It's too soon to say whether we can actually go there because we have to ask everyone involved. Yeah, but I hope it will be possible. I mean, of course, I would only go with one other person or so, but yeah, that's the plan.
Cool.
Yeah, Thomas, what about you?
Yeah, about me. So, stuff or work on the LPSC conference is continuing. Now, yesterday I had my last exam now for a while. Online exam, of course, so I now have time to prepare the talk and the poster for the conference. That's what I'm focusing on now. And yeah, in other news, the reason why I was maybe a bit overhyped at the beginning of the podcast was that in roughly 2 to 3 hours, 2.5 hours, Mars 2020, so Mars Perseverance, is going to land on Mars. And
Yay.
Yeah, I'm pretty hyped already. And I imagine I'm already really hyped, and I imagine what it would be like if you actually have worked on that rover.
Yeah, absolutely.
That must be. Yeah. So you've watched like the animations, how they want to land it with the crane technology that they used before?
Yeah, I think you shared an animation, I think. Was it on WhatsApp in your status? Yeah, I saw that one.
So it's like a jetpack with where the rover's attached, and then they let down cables where the rover's attached to till it touches the ground, and then the jetpack will fly away, like a crane. Jetpack crane, basically. And I love this method. It's, it is not, but it seems like they just want to brag about what they can do. It seems like so too complicated. Just look what we can do.
Yeah, absolutely. Sometimes landing techniques, not only on paper but in practice, they sound and look ridiculous. But somehow it works.
Why it is so.
Yeah.
I mean, there are reasons, but it is, this whole procedure makes it so much more. I'm so much more nervous because of this procedure, because there's so many things that can go wrong, right? The more parts you have, the more parts can go wrong.
Yeah, at the time we're watching it, or we're going to be watching it in about 2 hours, it'll already have happened.
Yeah.
So as soon as the footage arrives on Earth, it's already a done thing.
Yeah, and you've asked me about today because I made a 3D animation of the landing site. You asked me with what I've done that. I've actually done it with ArcGIS, so with the normal like one of the most standard mapping programs for geologists or planetologists.
Maybe you'll be able to share it somewhere?
I've shared it on Twitter.
Ah, all right.
So yeah, at TH and FH. But yeah. Hopefully. Okay, so that's about ExoMars. I thought about if I want to do like an extra episode on ExoMars today. However, because of all the exams in the last weeks, there wasn't really that much time to do that. But maybe we can get back to that at a later episode.
Yeah, I mean, of course, I think we're going to give updates next time, as we always do.
Yeah, I think also so. Okay, should that be our introduction, and then we will move on to our main part today?
Yeah, I mean...
Very short introduction today.
Actually, yes.
Okay, something new every time.
I mean, maybe you can talk on a bit more about the mission, except if you want to really preserve that for next time, maybe. Maybe we can dedicate some more time to that next time.
I think that's a better way to maybe go then into a bit more detail or something like that.
Yeah. All right, then.
We see you in the main part.
So, as we've said in the introduction part, today it's going to be a very, very different topic. In the past, we've talked about different kinds of rocks. We've talked about why the rock record is incomplete. We've talked about volcanoes, fossils, and today, actually, we're going to try something pretty different. And we're going to talk about diamond rain on ice giant planets like Neptune and Uranus. And actually, this is a bit kind of an experimental thing because Thomas is going to give us an overview over this topic. And then we're basically just going to see how the discussion develops. It was a pretty interesting topic Thomas wanted to talk about, and we've decided we just would like to try and see how this one turns out. But, well, how the hell did you encounter such a very specific topic?
Thanks, Dennis. Why did you say thanks, like in a talk? So that's actually a good question. And I actually want to turn that question. Did you have ever heard about that before? Did you ever heard about like diamond rain on Neptune or something like that?
Actually, I've always been interested in planetology and astronomy and basically everything that's out there. But to me, it was more elusive. It was more like that I had heard that there could be certain layers inside, in general, gas giants. I mean, you were going to talk about the ice giants, but in gas giants where, in theory, diamonds could develop and float around in these clouds. But I didn't know about diamond rain. That I never heard before.
Okay. Yeah, so that's actually the thing that's actually completely the same for me. I've heard about that before, like in the news or in podcasts or in video. I don't even know, but it's something that I've heard of before. But I've never really thought about it. It was just a back in my mind, staying there, and it's like, oh yeah, right, I've heard about that. But that's not the first time that I've actually tried to understand it and research it and to see what's actually behind it. And that's quite interesting. And also we come to the part to see what rain actually means here. There's some way that I can tackle that topic. I could just give you a small introduction or just a quickly talk through it and we would be finished in like, I guess, 15 or 20 minutes. But I think that we can get a bit more for discussion. So I first of all want to, as your question was, introduce why I actually come to the topic. So why do I even want to talk about the topic? And then I want to talk about the idea, the theory itself. And then we're trying to connect that with geology and why this is actually still important for us geologists and earth scientists. So that's the plan. Yeah, so how did I get to that topic? That's actually an interesting question, because I had in class, this is now my first year in a master, and I had a class called Physics and Chemistry of Inner Earth, where we talked every, I want to say episode, every week we talked about one specific topic, like for example seismology or convection or mantle blooms. And then in the same, or the week after that, we would have a seminar where one person should present a paper that our professor then would send us before. So if we talked about convection, then somebody could choose that he want to do a presentation about the topic, and then she would send us a paper, and then we would discuss it the next time. So while I was really, really interested in that class, like chemical physics and mineralogy isn't like the topic that I'm normally like work on. That's not something that I normally have so much to do with. And while I think that's incredibly interesting, I need a bit more time to get into it. It's not like something that I read and understand. That's something that I have to learn, to try to understand. And so I hope that I could actually get around that topic, that I could choose something where maybe mineralogy or physical chemistry isn't like that big a part of. And I've seen that the last lecture is going to be about exoplanets. So I thought, that's it. I'm just gonna wait for the last lecture, and I will choose exoplanets. So then, I got the paper like a week before the seminar, and I'm gonna read now the title of it: Formation of Diamonds in Laser Compressed Hydrocarbons at Planetary Interior Conditions. And I thought like, ooh, okay. That's not what I've expected.
Easy to digest, simple topic, no questions asked, perfect, brilliant.
Yeah, brilliant.
Easy.
So, when I read the title, I was a bit worried. Then I skimmed through the paper and saw that it was a lot about the methods and a lot about the chemical analysis. And I've got even a bit more worried.
Oh my God.
Anyway, I started to read the abstract, and then something happened. I have to admit that it's probably one of the best abstracts I've ever read. Because normally, I search for a topic, I'm working on something, I want to know something, I want to research something, I'm searching for a paper, and then I go through the abstract to see if that paper is interesting for me or not, right?
Mm-hmm.
So abstract is like a tool. But in that case, it was completely different. That paper was chosen for me, and I had to read it. So the abstract is not for me now like a tool to see if that's interesting for my work. It's about, can it give me an idea of what this paper is about? And the point is, I've read the abstract and it catched me. I've only read the abstract and it immediately got me very interested in the topic. And that was something pretty cool. So the paper, by the way, is from D. Kraus et al. So I read the abstract. And I said to myself, well, before I go now through like their methods, I want to research, I want to understand. And then I researched it. I researched it to try to understand it, to get an idea of the overall theory. And I, for example, found a really good article that we're gonna link at least in the YouTube description from the very author that wrote the paper, Dominic Kraus, on the American Scientist. It's a really good article, good read. He's extremely good in writing. Not only the abstract is good written. So, yeah, you could definitely check that out. So I got really interested in it and I researched it, and then I get onto the paper itself. And at that point, I was so curious about how they have done it. What experiments did they do? That actually the method itself, the part itself, was actually interesting for me. And I thought that was pretty cool. Have you ever experienced something like that? Like going onto a paper and suddenly being very interested by it, even if you haven't expected it?
Not to that extent, I think. But yeah, sometimes this happens. In my case, it happened when I, just as with you, I had to read something. It was for a report I had to write for stable isotopes, for the stable isotopes course. So isotopes, being different variations of the same element, but with different numbers of neutrons in their cores, but with the same basic chemical characteristics. And you can do a lot of different things with those. And one of those things is you can characterize what exact diets animals had by taking samples from their bones. And at first I shied away from some of those papers, and I always wanted to get into that, but I never really had the courage to do so. And then I had to do something like that for that course, and once I got into it, it was pretty awesome. Once you really understood what they were trying to get across, and once you just picked yourself up and got into it and just read it. Sometimes these papers, which sound pretty complicated and are more complicated, they aren't too bad to read, I think. I mean, often you're overwhelmed by the title, and then in the end, you notice that actually it's not even too bad.
Yeah, exactly. And that was the perfect example for me now going through that paper. Yeah, I mean, you know me, I basically can be interested in everything. Give me a most boring task and I will still find a small point where I'm like, oh, that's interesting, and then I'm gonna send you a 20-minute WhatsApp audio about it. But yeah, so I thought that was pretty cool, and I wanted to share that experience because, learning new things is always cool, but sometimes you're kind of afraid of, and then like seeing all these methods and it kind of scares you. Often it's still worth to go through it and try to understand it. Learning something new, even if it's like not in the topic that you normally would be interested in, can be a very cool experience. Definitely. Okay, so that's how I got to the topic. But now about the topic itself. Diamond rain. Now, what does that mean? That's the first thing I want to talk about. What does that actually mean? What is the idea behind that? Where does it come from? Why do we have that idea? Then I want to go into the methods. Now, I won't bother you with a really long explanation of the methods or like with numbers or anything like that. There's just some little basic things that I want to talk about. because it's an interesting question, right? I mean, we can go to these planets, so we have to bring them to Earth. And you have to be smart about that. And that's the interesting thing I want to talk about. Like the way they have to think to get to these experiments they're doing. And then, we try to see how we can fit that in a broader geological view. Okay. So let's start with the idea behind that. Now, as you said, we talk about Neptune and Uranus, which are ice giants. Now, first of all, we have to understand what ice giants actually are.
Planets.
And therefore...
It's my 2 cents.
Right. To understand that, we have to go very far back to the formation of our solar system, actually, if we really want to understand what ice giants are. Now, the formation of our solar system is following. We have a cloud of a molecular cloud, so a cloud of dust particles, and this cloud then gravitationally collapses in the center, and this forms then the protostar to our sun. And all the material around that from the dust cloud is then going to move, it falls to the sun, right? To the protosun, because of the gravitational attraction. But because these particles will keep the angular momentum, that's the preservation of angular momentum, they will start to rotate and form this disk, this protostellar disk around the sun. And this disk is the reason why all our planets today are all on the same line on the same disk around the sun, and do not orbit like in different angles than anything else. And this disk is very important to understand, because there are certain processes, chemical processes and physical processes in this disk, that will shape the solar system that we know of today. I mean, you probably know we have all the terrestrial planets close to the sun, and then far away from the sun we have these gas giants and ice planets or these ice moons like Europa, for example. So there are certain processes in this cloud that led to an uneven distribution of elements. And there are the many other processes that are very interesting for us, because we can use them like as fingerprints to understand where specific asteroids come from. Where did these asteroids form? Close to the sun? Far away from the sun? They're actually fingerprints, because we know some of these processes in these disks that we can use to understand that. Anyway, this disk has certain implications, as I said. And one implication is the temperature. Now, everything that is close to the sun is very hot, and it gets colder and colder the farther away you get. You can imagine lines that represent the decrease in temperature, and the farther away you get, the colder it gets. And at some point, at some of these lines, which is called the frost line, the temperature will be low enough for the formation of volatile molecules. So these are molecules that have hydrogen in their structure. For example, as water, or ammonia, or methane, or ethane. All these compounds, these light compounds that have hydrogen in their structure, they can only form behind that frost line, because this is like the lowest temperature for them, or the temperature for them to be allowed to form. Everything that is too close, the temperature is too hot, they can't form there. But they can form behind that frost line. And that's the reason why, all of our gas giants are in the outer solar system. They were created or formed behind that frost line. And within the frost line, we only have the terrestrial planets, because the silicate phases and rocks and anything like that, they could have been formed with much higher temperature. Now, these volatile elements, these are called, or volatile molecules, I should say, These are, on a geochemical side, these are called ices. So when we say ice giants, we do not mean like the state of matter. We do not mean ice as like, when water is frozen. But we mean volatile molecules, such as water, ammonia, or methane or ethane. That is called ices. And ice giants are basically just made out of a lot of these materials, a lot of these highly volatile molecules, a lot of these ices, and that's why they're called ice giants. And that's also why they got the blue color, because of methane.
I actually
in the
didn't know
atmosphere.
where the name came from. Yeah, it was
There you
usually
go.
just. I thought it was because they're that far out. Maybe they're gas giants beyond a certain distance from the sun. But yeah, interesting. I mean, that's of course the thing. Maybe at least the more planetology interested listeners might know that they are made up of these elements, like or not these elements, but the chemical molecules exactly. Like methane, ammonia, which are all pretty light in terms of atomic mass. So
Yeah.
I never thought about that, but very interesting.
There you go. And of course, also they have a lot of helium and hydrogen, of course.
Yeah.
So how have they formed? Well, there's the terrestrial planet formation, or planet formation as general. In this dust cloud, in this disk, small particles begin to accumulate and form planetesimals. You can just imagine like the dust particles are getting coarser and coarser and coarser because they are attracted by each other and accumulate. And once they reach like some kilometer size, they are called planetesimals. And then these planetesimals, there are a lot of them, and that's why they collide with each other and collide and collide and collide and collide. And that's why during a very short period of time, of probably even around 1 million years, these particles start to form planetary embryos. These are Moon to Mars-sized bodies. And then we have a lot of these planetary embryos in the solar system. And then over a longer period of time, because they are now very far away and they are less and less objects, they will form terrestrial planets by giant impacts. Like these large Mars-sized bodies will collide and form our terrestrial planets that we know of today. But in the farther solar system, so farther out in the solar system, there's something that was a bit different. These planets probably also have started with planetary embryos, so Moon to Mars-sized bodies. But then at some point, they collected all of these light molecules and gases. They collected all of the hydrogen, all of the helium, or not all of them, but a lot. A lot of the helium, a lot of the hydrogen, a lot of these volatile molecules. And that's how they have formed these gigantic gas giants and also these ice giants. And that must have happened really quickly, because we know that the sun itself, well, basically due to the solar wind, moved all of these light elements away from our solar system. And at some point, nearly nothing was left, because our sun has all thrown it out of our solar system, basically. And that's why they have to formed very early on. So, yes, there's still a lot of talk about planet formation, but that's basically the basics. And now we do know, hopefully, what ice giants are. Okay, but now we know what ice giants are, but why do we think that there's diamond on this planet? That seems like a far stretch. I mean, diamonds are pretty rare on Earth, right?
Yeah, they are, and they are only found in a very particular depth or on very, very few places on the surface.
That's correct, but The question is, are these rare in this or in our galaxy as a whole, or are these just rare on Earth or on other terrestrial planets?
Is this like an actual question, or am I just supposed to play the ball back to you?
Yeah, I want a good catchphrase, something like that. Spoiler, we will see that they're probably not that rare, and it's just on terrestrial planets. Yeah, now we know what ice giants are. And the interesting thing is that ice giants are pretty common in our galaxy. So a big part of all the exoplanets that we have found are ice giants. And I will talk about in the end how we can actually detect that, or how we can know that these are all ice giants. But yes, ice giants are pretty common in our galaxy. And as I said, they're mostly made out of light elements, or the light molecules that contain hydrogen. And that's why they're called ices. Now, they have an outer atmosphere that are mostly made out of hydrogen and helium and some methane. Then they have a mantle that can, on Neptune, get up to 17,000 kilometers to 18,000 kilometers. And this mantle is mostly made out of water, ammonia, and methane. And then we have a core that is probably made out of silicate and iron and nickel. Now, this mantle has extreme conditions, and I mean extreme conditions. We have pressures that are some several million times the pressures of our atmosphere. And we have temperatures up to several thousand Kelvin. We very close or very early on in the mantle get to temperatures that we have in the center of Earth. Or in retrospect, these are 5,000 Kelvin, and this is the temperature of the surface of the sun. And we get to these pressures actually very early on. So at 10,000 kilometers, which isn't not that much considering the size of these planets, we will already get at these extremely high temperatures and pressures. The pressure can rise up to not only rise up to, but the pressure is around 150 gigapascals already at 10,000 kilometers. So this is extremely much.
Especially considering that, basically everything up till that point consists of gases.
Yeah, exactly. And that's why the mantle, these ices, form like a hot and dense fluid. So that's a very weird state of matter. It's like very hot and dense and kind of fluid behavior.
That alone is pretty alien.
Yeah, it's pretty difficult to imagine. And this extreme state of matter, that's the interesting part. We've visited these ice giants only once, and this was with the Voyager 2 mission. And since then, this is now nearly 40 years, this happened 40 years ago, we have the idea of diamond formation on these planets. The point is, at these extremely high pressures, there happens something. Now, methane, for example, consists of carbon and hydrogen. And at these very high pressures, molecules like ammonia, methane become reactive. And they break apart, and hydrogen and carbon are going to separate. Normally, they are both very active to each other and form compounds, but under these circumstances, they break apart, they separate, and they will not react with each other. So we end up with isolated pockets of hydrogen and carbon. At least this is what physical chemistry tells us. This is like the theory tells us. And I guess you understand where I want to go with, because what happens if you have a lot of carbon on one place and you have very high pressure?
You get diamonds.
Yeah, exactly. We form diamonds. Because under these pressures, the diamond structure is the most stable form for carbon to be in. It's the best energy level they can be in under these circumstances. So diamonds should form, right? And then, well, diamonds are a lot denser than all of the surrounding weird liquid gases. And that's why they precipitate. They will sink. And they will sink till the point where they reach these inner silicate, rocky iron core. So they will basically sink to the core of the planet itself, where they will then accumulate, maybe, and form a layer of diamonds. That's the idea.
This sounds not only strange, but it also sounds as if it could truly alter the gas content over time. I mean, if you only take carbon out of the system, you never get it back. In theory, this should change the whole composition of the planet.
Yeah, I mean, probably over a really long time.
Yeah.
I guess there's so much stuff in there that it probably needs a very long time to show an effect, but yes.
Yeah.
It definitely has large influences on the planet itself. And that's also something I want to talk about later.
I mean, do we know whether there are... I mean, I think this is mostly based in theory. Is there any truly hard evidence for that?
There's some evidence for that, yeah. And that's what I want to do, or I want to talk about in the end, like when I try to combine everything that we know of.
Mm-hmm. Maybe just one quick question ahead then.
Yeah.
But would there also be some kind of a process recycling these diamonds?
Yeah, that's a good question, and we can't really answer that yet. So they're probably too heavy to be picked up by convection, as far as I understand it.
Convection by the gases, you mean?
Genau, yeah.
The liquid gas thing.
Yeah, the weird liquid gas thing. But we don't really know what the temperature is very close to the core. And it could be so high that carbon will melt, the diamonds will melt again, and then you would have like a weird layer of liquid carbon, and then things get weird.
Yeah, that's maybe a pretty good way to put it.
Yeah, so we're not really sure, but probably. Now, I think you also get where the idea from raining diamonds is coming from.
Yeah.
I mean, of course, that's like, is it raining? Is it sinking? It's like a weird mixture of gas and liquid. And I guess the term raining is just because it's like a catchphrase, you know? It's like, raining diamonds? What?
Yeah, it creates more of an image than sinking diamonds.
Yeah, exactly. I mean, you could probably argue about this is weird state of matter, right? It's like, is it raining? Is it sinking?
Who the hell knows anyway?
Yeah. Yeah, and that's the idea that came up back when Voyager 2 visited these planets, because we do physical chemistry, we do our measurements, or our, not measurements, but our calculations, and these calculations say, well, diamonds. And once we've created diamonds, all the other stuff with sinking and accumulating is then just basic fluid dynamics or something like that. So, as you said, is there some evidence? It's good that we have this theory, but can we test that somehow? Now we cannot just... First of all, we visited only one time, and probably is till the point that we have a new probe visiting these planets, it will take decades. And even then, we can't just enter these planets and see how their mantle is going to look like.
Yeah.
So the thing that we can do is try to bring these planets, or the mantle of these planets, back to Earth, or trying to create these circumstances here with experiments. That's basically the thing that we can do now to see what is going to happen. And there's some ways how we can do that. Now, there were some experiments before that already shown that it is possible. However, there's some problems with these experiments. And that's why there are always new papers. And that's why this this paper by Dominic Kraus et al. Is so important. Now, pressure experiments are pretty common in Earth sciences because we want to know how the Earth works, and we can just go to our mantle or like 30 kilometers deep down into our Earth and see what things look like there. We need some way how we can test that all these theories. And there are certain ways to do that, and I won't go into detail. There's so many ways, you could probably talk about that 2 episodes. But I want to focus on two that are interesting for the topic. Now, the first is the diamond anvil that you probably know of, right?
Yeah, I still remember that one.
Yeah. Very easy. You have a gasket of a metal, or like 2 gaskets that perfectly fit into each other. And there are 2 diamonds, very small diamonds. And these diamonds will then touch, and you screw them together. There are screws between these gaskets. You sample in between these diamonds, and then you will just screw by hand. That's the weird part. I remember when I first heard about these diamond anvil presses where you can like test material under circumstances like in the interior of Earth, and I've imagined like this gigantic machine. And then we were like in this small lab, and that's a handy device, you can keep it in your hands. And he had it in his hands, and he kept screwing and screwing and screwing, and I thought this was just preparation. And at some point he was like, yep, okay, so now we are at mental pressures. I mean, I can keep going.
Literally holding the world in your hands.
Yeah, basically. So yeah, that's a pretty easy way to get to high pressures, because the pressure is just now it just now depends on the force you keep on going. The force you keep forming by just screwing these 2 gaskets together, and the area of the diamond itself. But there are some problems with this method. So first of all, you get to high pressure, but not necessarily heat. No high temperatures. So you have to heat the experiment from the outside. And the second thing is, I mean, that's a problem of all of these methods, but you can only use a very small amount of sample, like really small amount. And then the largest problem for that experiment is the experiments that I've told before that has also already shown the diamonds can form under these circumstances. They were done with the diamond anvil. Now the problem is, once you get to these high temperatures and pressures, the sample itself is going to react with the diamond and the metal gasket. And well, that's quite a bummer, because this could influence all of your results. That's no closed system anymore. The sample is going to react with your experiment, then well, that's probably going to influence the results. And that's why we need other ways to do that. And the other thing you can use is shock compression. Now you can think of what shock compression is.
I mean, I can imagine what it is, but I don't have any specific research method in my head right now.
So one explanation? You have your sample and you shoot at it.
Oh.
You have your sample, you have a projectile, and you shoot it against the sample. That's the idea.
I think pretty small projectile, pretty small sample.
Yeah, of course. There are many ways how you can do that.
Cannonball sized.
I mean, that was done before, right? Like testing meteorite impacts, that you just shoot cannons at some weird material. Anyhow, there are some problems with that method. So first of all, it's very easy to get at high pressures, right? I mean, if we go into meteorite craters here on Earth, we can find weird minerals that only form like under really, really high pressures. And getting to high pressures or getting to specific pressures is also not difficult because it depends on the speed of the projectile, and that we can control. However, it's very difficult to control the temperature. There's like no real way to get the temperature to the exact point that you want to have. And the problem is the temperature can easily get so high that diamonds will melt again. So you maybe would have formed a diamond, but so hot that they just melt again.
It sounds as if it's not easy to do all of this.
No, it really is not. And that's why you have to be smart about it. And there is another way how you can do shock compression. You can use high energy lasers. Like energies with a really high lasers with really high energy. Once they reach the sample, they have a similar effect to a projectile. And with lasers, it's a bit easier because you can use like a different amount of energies, like different energies, and you can also use like not only one shot but more shots than one. And that's what they've done. So they used like first of all they used a laser with a lower energy, and then they used a second one directly after that, like 6 nanoseconds after that, with a higher energy. And with that, they're actually able to keep or to get the pressure higher and higher and higher, but the temperature will only increase very slightly. So they can actually control the temperature with that. Like the pressure is increasing by a factor of 2 or 3, and the temperature only like by 10 to 20% after the second shock. And well, you can think of that's very high technology, so that wasn't really doable some years ago.
It sounds pretty futuristic because,
yeah,
I mean, this is also a point which I could understand if not everybody is truly on board with that, in case that you don't really know more about this technique, because shooting something with a laser and then saying that this can simulate pressure, it sounds pretty strange at first, I think.
Yeah. It basically definitely is. But I would say like at this point, I do not want to go into more detail. Like that's something that you can research if you want to, but
yeah. No, I just wanted to address this because I think this is a really important point, because
definitely,
like, it's just something in which case I could understand if someone feels really that doesn't really know what to make of this, because to be fair, it sounds pretty it just sounds pretty strange.
Yeah, it really does. It's a really complex.
Yeah.
A really complex method. Yeah. Yeah, but we encounter a second problem with that method, and that's time. Because if you shoot something whether you shoot a projectile at something, then you will get to high pressures, but of course only for a very, very short period of time. The conditions only last for a billionth of a second. So the next problem is, then how are you going to measure what is going to happen? That was not possible for many, many years. But since 10 years, we actually have methods to do that. These are called X-ray free electron lasers. And again, I do not want to go into detail with them. I don't also have the knowledge to like really go and explain how they exactly work. But a special part about them, and that's important, they can make measurements, extremely high resolution measurements, in extremely short periods of time. And that is, they can do measurements within a femtosecond. Now, a femtosecond is 10 to the power of minus 15 fraction of a second.
That's pretty short.
Yeah, that's incredible. I was I was really baffled when I read that.
Honestly.
So, yeah, it's really astonishing how far we get to that point. I mean, to explain X-ray diffraction so you know what we're talking about, you shoot X-rays, basically, or electrons and onto your sample, and then you're gonna look at the X-rays that are diffracted by that sample. And like every mineral or any elements and phases, they have different patterns of these diffracted waves. And that means that they are like fingerprints that you can look at your sample, you see like the diffraction pattern, what's called, and then you can just compare it to large, well, like in large, what's it called where you store books? Library.
Ah, okay.
A large library, basically, where there are a lot of different measurements were done, where the results of different phases, and you can just compare it, and then you see, oh, there it is. And I mean, I've done X-ray diffraction kinda by myself. We had like in Cursor, we learned to do that. The problem was that the X-ray diffraction, or the machine was actually not working then we simulated it. We like put a sample in and made noises. Then we looked at results that we have done before. But normally it takes some time to do that. And now we can do that just within a very short fraction of a second. And that means that even if these conditions only last for a billionth of a second, we have enough time to see the results or to see the evolution. Not just one measurement, we can see the evolution of the material over time. So we see what happens over time just within a billionth of a second. And that's incredible. So yeah, that's what I've done. So they used like a polystyrene, carbon compound with a lot of carbon, a lot of hydrogen. Then they shoot these lasers against it and, well, looked what happened. They simulated conditions to a depth of 10,000 kilometers. That is 5,000 Kelvin and 150 gigapascals. So that's all I want to talk about the method. I just thought that it would be cool to show how difficult it actually is and how far we have proceeded and how smart you have to be when trying to tackle these problems that we have.
It's pretty interesting because once again, it's now that you've said it, I'm like, yeah, all of this makes sense, but it's really astounding how much thought has to go into that. I mean, for instance, going in, I mean, I knew about some aspects in terms of the method which you were going to talk about, but I gotta say, I didn't really think about all the problems you could encounter. And that's pretty interesting to hear.
Yeah, and all these measurements, they weren't able to be done like a bit over 10 years ago. It was not possible to do that. The first X-ray free electron laser opened like in 2009. And yeah, before that, it was absolutely not possible.
All right.
Yeah, so what are the results? The results are, well, we form diamonds. Very small, tiny, nice diamonds. And actually, it shows us the theory is right, because after the first shot, we see that carbon and hydrogen get compressed, and we have this weird liquid, where it's like separating from each other. And then after the second shot, when the density is increasing strongly, then we see we will form diamonds. Very, very small diamonds, about 4 nanometers. So, I mean, it was a very small sample, but still like very small diamonds. So, that's it. The experiments say we have diamonds. But what does that mean, right? So we saw that there are different methods now, and all produce diamonds. Now we have a better method to do that, and it still shows us to get diamonds. There are, of course, some different results from that paper to like experiments that we've done before. They showed that happened in different pressures at different temperatures already. So there are some changes with these. Yeah, some changes in the exact circumstances, conditions that have to be present for diamonds to form. But the important part now for me is, okay, we've shown with the experiments the diamond form. And I think we can now ask ourselves, what does that mean? You know, it's nice to have, but what does that now mean? What are the implications onto these planets, onto reality? How can we even compare the results to reality? And then the question is, and I think that's the part that you also want to talk about. Normally in geology, we talk about rocks. So what does this mean now for planetology, for planetary sciences, for other planets? What are the implications? And there are some. Remember that is a paper about exoplanets, and I've only talked about Neptune and Uranus so far, and that has a reason, because I will come to that later. Okay, so first of all, what does these measurements mean? If we compare these results to the thought, and that's important, to the predicted environments within these planets. We can't measure them, we predict them. And we see that it fits. So if you look at the phase diagrams, which means that you have pressure and temperature in a plot, and you basically see with lines the evolution of temperature over pressure. And we see that, yeah, under these circumstances, and these conditions in the experiments, they also are probably present on Uranus, on Neptune, and interestingly, even on Jupiter.
Oh.
Now, I've not gone into detail with Jupiter, so I don't know what the idea is with Jupiter, but I know that there are some other weird things going on in Jupiter. For example, metallic hydrogen. Completely another topic. So I don't know if they think that this probably also happens on Jupiter, but at least the environment would be there. So that's interesting. Yeah, and they've also shown that it's important that the temperature is not allowed to be too high, because at some points diamond will melt again. They've made some. That was like a bigger part in their paper where they talked about it's important not that the temperature is not too high, but we actually think that the pressure is like at relatively much higher than the temperature within these planets. So it seems like if we try to modulate or try to predict the interior of these planets, then yes, these experiments could actually show that this phenomena could also happen on these planets, not just in experiments, but it seems like this is possible. Of course, these planets are much more complex, and there are probably many different processes within this planet, but it seems like a good guess. And you've asked about hard evidence. So that's where we now want to look at these planets itself. Now, there are some interesting things about these planets. One is that if we look, for example, at Neptune, it emits more energy than it receives from the sun. So there seems to be a process within Neptune that emits energy.
Yeah, that sounds.
And that's a weird thing. Yeah, what do you want to say?
I mean, I'm very positive right now that this is a good sign, because if something emits energy, this energy has to come from somewhere, and when diamonds form, they usually release energy because this ordered state the diamond state in which the atoms are arranged a certain way has less energy than free carbon. It releases energy while forming diamonds.
Exactly. So that's the first point. Diamond formation should release energy.
Oh.
And also, like on a physical level, when they precipitate and start to sink, they will interact with like friction with all the material around them. And that should also release heat.
Yeah.
So that could be a good sign. Again, there could be other processes, of course, but that's actually a really good sign.
Yeah.
And then there's another interesting thing. These planets all have these surprisingly violent storms.
Mm.
And these storms also need, well, an origin. They need an energy source. So that's also an interesting question. Would be the energy that could exist or could be created during these processes actually account for the storms that we see on these planets?
Diamond rain on Neptune creates unimaginably alien storms with apocalyptic implications. I can see the paper right now.
Yeah.
Honestly, this I'm really just smiling around right now because this is pretty cool. Because I mean,
Yeah.
of course, it's just a theory at that point, but at the very least, it's something where you can now be like, huh, maybe we should look into that in terms of
exactly.
more direct data.
And I love that. It's just, it seems like two complete different things. Like, okay, it's emitting more energy, and okay, we have the theory about diamond formation, and suddenly you're like, wait,
Yeah.
could it actually be? Yeah. So that's the first. I put it in quote hard evidence, but it's the first evidence we think there could be. And then the second one is the magnetic field, because they have a very weird magnetic field. It's not symmetric, and they do not extend like from each pole, so they're very unsymmetric and ununiformly formed. And that's also a weird thing because, I mean, very high pressures, very high temperatures, there's probably a lot of convection going on, so shouldn't there be like a large symmetrical magnetic field like Earth has? And the idea is that if you would have like a conducting material around the core, even if it's very thin, then it could influence the magnetic field. And I told you before that there might be, I mean, if all the diamonds are sinking or raining, how you want to call it, to the core, well, they're probably gonna form like a layer around the core. And so maybe the maybe the magnetic field is influenced by this layer of carbon that exists at the core.
Yeah. Oh man, that's really really interesting. And I mean, I don't remember right now. Is this the case for both Neptune and Uranus?
Yeah.
Lines of evidence?
Yeah. As far as I don't know the energy on the Uranus, I have to admit, but magnetic field is weird on Uranus and Neptune.
Yeah.
And the energy I only know of Neptune. I don't know of Uranus, but I can look that up maybe for the next time.
Yeah, I mean, but at the very least, if both show same weirdness in their magnetic field, that's at least something where it can be like,
yeah,
intriguing.
That's very intriguing. So that's the quote hard evidence that we think we may have, like the large topics. But now the question would be, we talk about geology, or earth sciences. So what does this have to do with earth sciences? That's something that you, for example, stated like in our WhatsApp chat. We're like, maybe we should like talk about that and to see like what does it have to do with, well, rocks, basically?
Yeah, probably because it has to do with geology, because of course diamond formation is something that is going on our Earth and
Yeah.
well, terrestrial planets in general as well, but in a completely different way. I mean, it's not raining diamonds here.
No. Yeah, and that's the point. I mean, at planetary sciences, you look at planets, and well, there are rocky planets, and there are planets made out of gas. And while they have very different processes and they look very different and all that stuff, at least in the end, they have all in similar formation. We all have the same origin. The evolution of all of these planets was different, but they all have the same origin. So understanding all these processes and like all these weird things, weird nicks, or nicks, not the word I was searching for, or weird things about these planets, they can give us an idea about maybe even how they have formed in the first place. So understanding the interiors of these planets can give us an idea about the formation of these planets, the planets itself, and therefore, for example, the origin of them. And we know that all our planets have a shared origin, and this is this protoplanetary disk. So this could even give us some new details into the formation of planets, as far stretched as it may seem. But understanding, and that's something that I've learned in that course, is that understanding the different processes in the interior of planets actually has large influences on the formation of these planets, because there's certain boundary conditions that we have to presume or to assume, and therefore these have implications on the formation. So that's the first thing. Then a second thing is, of course, geologists try to understand what Earth work, or how Earth's interior looks like, what processes are going on there. And in the end, well, these are also planets, so there is like, you can might not like say, okay, it's geology when you look at the interior of Earth, but it's not planetary sciences when you look into the interior of Saturn. You know what I mean?
Yeah, I can follow you here.
Yeah.
Everything is connected, basically. Everything goes back to the same origin. It's like, looking maybe at bacteria on the one hand and at foxes on the other hand in the animal kingdom. They all go back to the same origin, despite the fact that they don't really have much in common anymore. Everything what makes them up had one common origin, and you have to go back to that origin sometimes to understand specific questions.
Exactly, that's a really good analogy. So that's the first part. And there's also a second part to it, and that's where I want to talk about exoplanets for a brief moment. Now, exoplanets are planets that orbit other stars, so stars that is not our sun. And, well, you can imagine that we can find these planets, but the data we have is very limited. I mean, for example, we can measure them by looking at the star itself and seeing how the star flickers. So like when the energy release is getting lower, then the planet is like moving in front of the sun, and when it's getting higher again, the planet has moved next to the sun. So we have very limited data, but we know two things about these exoplanets. And the first is the radius. We can measure how large they are. And we can derive the mass. So we know radius and mass of these planets. And well, we try to work with everything we have. So let's try to see if we can actually learn something about the planets with radius and mass. And the thing I want to come to is, if you, for example, have made an object that is mostly made of rock and a bit of iron, like Earth, then you would have a relatively large mass, at a small radius, right? It's dense material.
Mm-hmm.
But if you want to have the same mass with, like, for example, water or ice, then you would need a bigger radius because you would need more material till you get to the mass. You understand?
Yes, indeed.
Okay. So what we do is, well, we have our solar system as like anchor points, and then we just look at, okay, Jupiter has this amount of gases, maybe these amounts of rocks in the interior, anything like that. It has this mass, it has this radius, so it's somewhere plots here. And with these like correlations, we then can look at the exoplanets and like plot them in a diagram with, well, radius and mass. And then we can see, where do they plot? Are they rather small but have a high mass? So then they're probably Earth-like, or at least like a terrestrial planet. And are they really large? Maybe have a high mass but a relatively very large radius? Then they're probably made out of gases. And this is, at least to some degree, pretty precise. So there are actually a number of different planets that we can, or that we think we can try to classify with that method. And, well, such an, for example, information of diamonds would definitely change. Like, the diamonds are much more denser, right? So it would definitely have an influence on like the radius to mass ratio. And when trying to modeling that, you see that this would like lead to weird jumps and kinks within these diagrams. And that's why that actually has implications on classifying exoplanets. Because it could be that exoplanets that we would have classified differently first, and we know that many exoplanets are ice giants, that maybe some are even wrongly classified due to this weird relationship. So maybe we can get even more precise when classifying exoplanets with this relationship that is based on the formation of diamonds. So that does not only have influences on the understanding of the planet, the understanding of our solar system, but it even has influences on the understanding and study of exoplanets. And I hope I was able to explain to you why on paper that when I read it my first time, I thought I was worried about, ended up being so fascinating for me.
Yeah, 100%. And I'm once again pretty thankful for the podcast, because otherwise, I mean, you shied away from the title. Otherwise, I would never have read that, and I would never have learned about that probably. So, yeah, that's pretty exciting and pretty awesome.
Yeah. That paper, I don't know, it was just going from, okay, should have chosen another one, to researching it and, well, want to make a podcast about it. That's a cool path that I've taken there. And yeah, I don't know, sometimes in science you also have to maybe go out of your comfort zone to learn new things that maybe can even help you in the end. I don't know.
Yeah, totally. This is what I was trying to say earlier as well. Sometimes it's these courses where you're forced to try and learn something new, to research something you usually wouldn't research. I mean, it doesn't go too well all the time because, as both of us know, some subjects are just not really something for you, and in that case, that doesn't help much. But instances like these, where you're kind of interested, but maybe you shy away because at first you're like, oh my god, this is going to be too complicated, and often this helps open your own eyes. This often helps to show you that, hey, you can understand, or that maybe these things which seem very, very complicated at first, you can understand them with maybe not too much effort, with just researching some things. And this can be a very encouraging feeling, a very encouraging experience. And I mean, I think we're both guys. We started reading papers pretty early on, so we
Yeah,
were
I guess so.
we were already pretty familiar with reading papers early on. But yeah, honestly, often I think that students shy away from reading papers, and I mean, it is technical literature. It is sometimes more difficult to understand, but experience like these, which are pretty important, that you invested into something in the first place.
Yeah, definitely. And especially maybe also in your field that you're working on. I mean, it's not directly you, but all of us. Um, Sometimes there are things like new methods that we can learn of that we were afraid of before. That's for me often things that involve well, informatics, computer stuff, where I was a bit, I don't know, careful at first, or a bit shied away from it. But in the end, ended up using it because it's a very good way to do you whatever you want to do.
Yeah, the same with me. I mean, I am even less of a computer fan than you are, to say the least. And now that I've gotten into some more of that stuff, yeah, once you've just found the courage to just go ahead and try it, I mean, what do you have to lose? It's often it takes me a long time until I really try something new, until I really find the courage to try something more complicated. But in the end, it's so rewarding. It can be so fascinating once you get behind all that.
Yeah, sometimes you have just to put energy into it, and once you get like over the, yeah, I don't know, over the wall, once you understand it, then it's like a completely new field that you can now work on or try yourself into. Yeah, and the other thing is, it's just found it so interesting that such as, like, it was a pretty short paper, and like, even if it does not seem the way, like 80% or 70% of the paper were methods.
Sounds
Maybe
like
not,
it.
yeah, maybe not 70, but 60 to 70%, something like that. And then there were a lot of results and a lot of discussion about the X-ray diffraction that I've actually um I actually get into detail with the analysis because I used it for the talk I've given, for the presentation I've given in class,
Mm.
um, which I did not want to do it now in the podcast. But I don't know. I just found it interesting that such a paper where it's like only methods and analysis. That's why I mean that's the reason I was afraid of. I was shied away. Ended up being having such large implications on so many things.
Yeah. I mean, it's, of course, one has to say that, I mean, I'm not someone in that field of research, so please bear with me if I might say something which isn't entirely true, but I mean, my feeling is it is still on a theoretical basis. It
Yeah,
could be going
definitely.
on there, but yeah, it's like with the phosphine on Venus, which has been reported earlier last year, I think mid last year.
Yeah,
Um,
with last year or something like that.
it's these are proxies. These are reasons to get people to invest more effort into
Yeah,
researching these aspects and to either find evidence for or against these theories. But yeah, I think these works showing that, hey, in theory, XYZ could be going on there, these are pretty important. Because these create discussions, these create talking among specialists, and these create more experiments. So I really enjoy these papers.
Yeah, the thing is that often the I don't want to say general public because it sounds like arrogant, but I mean like people that are not really in sciences, that's often very difficult to understand for them what scientists mean when they conclude something or they make theories about something. I mean, even I about that topic, Diamond Rain, as told you, I heard about it before. And for me, it was like, I always had in mind that it may have could been just like an, not media outcry, but, scientists gonna say like, oh, we have the idea that maybe theoretically it is possible that it could be. And then the next thing you read in the media is scientists has proven. But that's not how science works.
Yeah, there's a whole Big Bang Theory episode about that very topic.
Really?
Yeah. I mean, I'm not really the biggest fan of Big Bang Theory. I think some of the jokes about science and how scientists conduct themselves among one another and things like that, and these in-jokes about different disciplines. This is pretty. For that, I like it a lot. But my girlfriend watches it on a pretty regular basis, and there's one episode where Raj, I think, where he has a talk, and in this talk, he, I think, states that, yeah, in theory, there could be life out there. And then it starts this whole media outcry, with titles like "Scientist says there are aliens" and stuff like that. And he spends the whole episode trying to somehow get over this media outcry because he said something wrong one time, and he really said it like careful. He was like, "Yeah, in theory, who knows? Maybe there could be something out there." The media just twisted it into their personal message, their personal headline.
Yeah.
And then in the end, at the end of the episode, he has another talk. He once again says or suggests something, and I think once again it's twisted into something different.
Yeah, I mean, it's like you have to understand what science want to tell you. This all now with Diamond Rain, it all seems so, it works in the method or in like the experiments, and we see some maybe evidence for that. And yes, but no one is claiming that's it. That's it. We have figured it out. That's the reason with Diamond Rain. That's nobody claims that. At least I think so. It's about we have this idea. It seems to work. We have new results, new evidence, but we need further work. And I mean, they use that work also to advertise for new space missions because they also want to figure it out. That's why they're working on that stuff. And they're like, okay, we need new probes, new space missions to these planets, and then maybe we can find out more. Our data is very limited now, and maybe with new missions we get new insights and new results on that topic.
Yeah, absolutely. Yeah, so now all we need is a spacecraft and a couple of years' time. And a lot of money.
And
but let's go to Venus first. Or Mars.
I want to go to all of them on the same time.
Yeah. We'll just do a quick gravity loop and then we'll just slingshot ourselves around the solar system.
Yeah.
Yeah, but pretty cool. Honestly, I really enjoyed that.
Yeah, I'm happy about that. That you enjoyed it, and I hoped when everyone was listening till the end, I hope you learned something and you found it also enjoyable. And Yeah, I also enjoyed it, which is a really fun topic, and I love talking about it. So, is there something you want to talk about still in the end?
Honestly, I think I'm pretty happy with this episode the way it is. It's a little bit of a shorter one, but that's okay.
Which is not bad.
Exactly. I mean, maybe we can just add this very quick little session about maybe plans, ideas for next episodes and stuff like that. Maybe a bit of planning because we have desperately been trying to maybe shorten the episodes up a bit.
Yeah.
We have, I mean, we both really enjoy long podcasts. So we're both kind of guys we like to listen to longer podcasts. I mean, I think me more than you.
Mm.
You listen to shorter ones, or do you listen to?
I mean, like the main podcast I'm listening to is about 1 to 1.5 hours, so
Yeah.
it's also. I think many people think that's pretty long.
Yeah, but
Yeah.
case in point, we really like this long format because, yeah, I mean, we record conversations. This is not really us trying to deliver a perfectly formatted, researched, and completely planned through thing to you guys, but this is really more us having a discussion about things, an organized discussion, and I would like to keep it that way for the most part, I think.
Yeah. Yeah, I like that style.
Yeah, but I don't know, maybe we'll do some shorter formats. Um, we are going to experiment with a couple of things this year, I think. That's at least the plan. But maybe just to explain, we have been trying to really maybe shorten episodes till at max 1.5 hours or something like that.
Yeah. I
This
like how we used like 5 minutes now for the segment instead of we desperately trying to shorten.
just highlighting the problem here.
Yeah.
But just to explain that,
Yeah.
I think we're both at home with this long format. We'll still try to shorten episodes up a bit, but we'll see how things develop. Maybe we could in the future do some other kind of shorter format for little things we just want to talk about. Who knows? We'll see, and we will try something this year, I guess.
Yeah, definitely. So, if that concludes our podcast for today,
Yes, I would say so.
then thanks for listening, and we see each other next time.
Bye, guys.
Bye.
Thanks for listening to the RockyTerrain Podcast. If you enjoyed listening to us, please consider subscribing on your favorite podcast platform. Everything addressed in this podcast reflects our own opinion. You can contact us at 4.5gainthemaking@gmail.com. That is 4.5gainthemaking@gmail.com. All music used is from Kevin MacLeod and was downloaded from filmmusic.io under the Creative Commons license. That is heavy interlude for intro and outro, and home bass groove for intermission.
Wir haben, glaube ich, gar nichts für. Oh, wir haben kein German Word of the Day. Krachmacher. Someone who likes to make a lot of noise and who annoys other people with it.
Okay, that's now going to be at the end of the podcast.
Yeah, we missed the German Word of the Day.